Hi, I'm Huey, and this is my part on Avogadro's Law. So we're going to start off with Mr. Charles Frederick, who's a great physicist, and Auguste Laurent. They were the first ones to demonstrate Avogadro's Law, which explained why the same quantities of molecules in a gas have the same volume. But their experimentation did show that some inorganic substances showed exceptions to the law. So this contradiction was eventually resolved later and was announced at a Congress of physicists in 1860. Unfortunately, 4 years after Avogadro's death, they explained these exceptions were due to molecular dissociations at certain temperatures, and that Avogadro's law not only determined molecular mass, but atomic masses as well. So an example of this in everyday life would be like blowing up a balloon, and a balloon's volume would increase as you added moles of gas, so when you blow it in. And then similarly, when you deflate the balloon, the gas leaves the balloon and its volume, of course, shrinks. So the difficulties with Avogadro's law and complications, real gases versus ideal gases, like we were talking about earlier with different temperatures, non-gaseous states, mixtures of gases can also cause some difficulties and complications, and temperature and pressure conditions, of course, and measurement accuracy. It was hard to do back in the 1800s, and molar volume variance. A lot of that was hard to do back in the day. It's easier now because we have a lot more technology, and this is just a picture describing the Avogadro's law, the formula for finding it, and also what we talked about earlier with different pressures here. So, motivations for finding Avogadro's law. With finding Avogadro's law, you can define the mole, more measurement precision, quantum considerations, applications, of course, in different fields, which is really cool. Like today, we have nanotechnology and biochemistry, teaching and learning challenges. Sometimes grasping it is, for me, it was kind of hard, but putting it in simpler terms helps a lot now. And it helps the scale and microscopic world and how it relates to macroscopic quantities. And it has a connection to many other constants too, like Boltzmann's constant. And understanding these relationships can be essential for deeper scientific analysis, but also adds layers of more complexity. And once again, we're showing Avogadro's law here. Equal volumes of gas at the same temperature and pressure contain equal numbers of molecules. So we've got hydrogen, oxygen, and carbon dioxide, and how they all have the same number of molecules inside. You can see here, here. They may be in different areas, but they're all the same amount. And finally, what are some of the benefits of discovery of Avogadro's law? So now we have a better understanding of molar volume, stoichromatic calculations, gas mixture analysis, we can do that better, support for ideal gas law. We have a lot of applications in medicines now, and which is really important in anesthesia and respiratory therapy, material science innovations, and research and industrial applications. And once again, this is showing same temperature, different oxygen, hydrogen, vapor. They're all moving, but they all have the same amount of molecules inside of them. And once again, we have Avogadro's law and how to use the formula to get it. And that is the end of my part, and we'll move on to modern experimental process next. Thanks so much.
1.2 Avogadro's Law. Avogadro's Law is a statement that under the same conditions of temperature and pressure, equals volumes of different gases contain an equal number of molecules. There is also Avogadro's number, also known as Avogadro's constant. It is a specific number of molecules in 1 gram mole or substance, defined as a molecular weight in grams is 6.22140076 times 1023. So in the original experimental process, experimental studies carried out by Charles Frederick Gerhardt and Auguste Laurent on organic chemistry demonstrated that Avogadro's law explained why the same quantities of molecules and gases have the same volume. Nevertheless, related experiments with some inorganic substances showed seemingly expectations into the law. This apparent condition was finally resolved by Stanislao Cannizzaro, also announced at Karlsruhe Congress, 1860, 4 years after Avogadro's death. He explained that the expectations were due to molecular conditions at certain temperatures, and that Avogadro's law determined not only molecular masses, but atomic masses as well. An example of everyday life in Avogadro's law would be blowing up a balloon. The balloon's volume increased as you add molecules of gases. Similar, when you deflate a balloon, the gases leaves the balloon and its volume shrinks. 3.1 Modern experimental process described. Avogadro's law states that equal volumes of gases at the same temperature and pressure contain an equal number of molecules in modern experiments. Gases samples are often analyzed using advanced techniques like gas chromatography or mass spectrometry. These methods allow scientists to accurately measure the volume of masses, gases, providing precise data to confirm Avogadro's law. 4.1 Relevance of questions and topic explained. An example question could be, how does Avogadro's law apply to real-world scenarios, such as calculation of gas mixtures? This question is relevant because it connects the theoretical aspects of Avogadro's law to particular applications, helping to illustrate its importance in everyday life and various scientific fields. 5.1 Relevant graph chart and diagram. This graph helps to understand the relationship between volume and the moles of gases. This is important to the equations that helps to determine the moles in a gas when doing calculations gas reactions.
Hello everyone, my name is Zoe Cox and I am in the Avogadro's law group with Huey, Ricardo, and Zachary and myself. I completed slides 10 through 17, but today I'll be going over slides 5, 7, 11, 15, and 19. Alright, let's get into it. Alright, so slide 5, it's the relevant scientist for the Avogadro's law, and it reads, the Avogadro's law was discovered by scientist Amedeo Avogadro and was related to the ideal like old contemporaries like Joseph Louis Gay Lussac and John Dalton. The Avogadro's law difficulties and complications. So, the numerical value of Avogadro's number cannot be detected from purely theoretical considerations, but must be determined experimentally by somehow counting this number of entities in 1 mole. Real gases versus ideal gases. Avogadro's law applies to ideal gases, which does not exist in reality. Real gases deviate from ideal behavior under high pressures or low temperature due to intermolecular forces and the volume occupied by the gas molecules themselves. Non-gaseous states. Avogadro's law is specifically for gases, so it doesn't apply directly to liquids or solids. In these states, the relationships between volume, mass, and the number of particles follow different principles. Now, mixtures of gases. In gas mixtures, each gas exerts its own partial pressure, and the total volume may not correspond simply to the sum of individual gas volumes, especially when considering interactions between different gases. The temperature and pressure conditions. This applicability of Avogadro's law is limited to certain temperatures and pressure ranges. Extreme conditions can lead to significant deviation from the expected behavior. Measurement accuracy. Accurate measurement of volume, temperature, and pressure is crucial. Any errors in the measurement can lead to incorrect conclusions regarding the number of molecules. Molar volume variance. The molar volume of a gas varies slightly depending on the type of gas in these conditions. Temperature and pressure which can introduce complexity in calculations. Did I already do measurement accuracy? Measurement accuracy. Accurate measurement of volume, temperature, and pressure is crucial. Any errors in the measurement can lead to incorrect conclusions regarding the number of molecules. We are now on slide 11, which is differences in modern approach outlined. In the past, experiments relied on simple gas collection methods and measurements. Today, the use of technology has improved accuracy and efficiency. Modern approaches utilize computer simulations and automated data collection, which reduce human error and allow for a real-time analysis in gas behavior under varying conditions. So, and here it also shows like the different, I guess, like the difference between Boyle's law, Omiton's law, and Avogadro's law. It's just showing like the baseline, and then it's like saying on Amonton's law, it's heated up or whatever, and the increased pressure. And then on Boyle's law, the volume's decreased, and for Avogadro's law, it's more of a constant increased volume. Okay. So now we're doing slide 15, and this is going to be the benefits of understanding question given. So understanding this question allows students to see the practical implications of Avogadro's law. It helps them grasp how gas behavior affects industries such as pharmaceuticals, environmental science, and engineering. This knowledge can foster critical thinking about how scientific principles apply to the real-world problems, enhancing their overall comprehension of physics and chemistry, which is so true because I do environmental science, and I do think there's a lot of physics and chemistry both involved in the real world of it. Alrighty, so now I'm going to be doing slide 19. This is going to be the relevant formulas and constants. This states that volume and moles of gas are directly proportional and give you the formula to figure out how to compare the same gas at different conditions. This also helps scientists to figure out how much moles of gas there are. The stoichiometry's formula are used to help scientists to calculate the changes that occur with gases mixtures. So thank you for listening. We are the Avogadro's Law Group. I'm Zoe Cox, and thank you for listening.
Hello everybody, I am in the Avogadro's Law lecture group with Ricardo, Zoe, Huey, and myself. And then I did 6.1 through 4, and those are the only slides that are left to be read, so let's get into it. 6.1 reads, the Avogadro's law only applies when the pressure and temperature are kept at a constant rate. The relationship between pressure, temperature, and moles, the number of moles, are that if you double the volume, pressure, and temp, the number of moles will also be doubled. Avogadro was also heavily influenced by John Dalton's atomic theory, which aided him in the distinguishment between atoms and molecules. The law first came about in the early 1800s. Amedeo Avogadro presented this to higher-ups whenever he first gathered this information at the University of Turin. The higher-ups kind of brushed this off, and then it was later accepted in the mid to late 1800s when Stanislao Cannizzaro revisited his work and topic to later make it what it is known as today. Avogadro's law is a direct relation between the gas's volume and number of moles with a constant pressure and temperature. The temperature and number of moles will always be proportionate, whereas if the temperature doubles, the number of moles will also seem to be doubled as well when you measure them. And then a good equation to Avogadro's law would be V1 over N1 equals V2 over N2. And then 6.4 is a list of our sources from numerous different websites and articles and books and all that of the sort. Thank you.